Welcome back. In this lectures, we are going to discuss the discrete state space systems, controllability, observability, and different representation of the, or we can say the canonical representation of the discrete space system. So before proceeding these lectures, we just going to recall the previous lectures. In previous lectures, we already discussed the state space systems and its calculation steps, and we already apply the state transition matrix calculation using the state transition matrix using Z transform, then Cayley-Hamilton theorem, then inverse Z transform. Then we already discussed the few examples. So this is the already covered in previous lectures. So in these lectures we are going to develop or define the controllability and its test, observability, and then what are the conditions to test the observability of the discrete space system. Then now we are going to represent the discrete space system in controllable form, then observable form, then Jordan form. These three forms are basics we are going to cover in this lecture. So first we are going to define the controllability. So controllability means if there exists an input UK is the input in discrete form where k is varying from 0 to n minus 1 with n as a finite positive integer which transferred the initial state x naught to the state x1 at k is equal to n, the state x naught is said to be controllable. Means with the help of input we can transfer the state, only one state from the initial value to the other state value, that is the x1 in within a finite duration. If all initial or of initial states are we can transfer from the initial state to the other states, then we can say that this system is a completely controllable. If it is not happen, then we can say that system is a uncontrollable. So here the definition they are telling this which transfer the initial state x naught to the state x1 at k is equal to n. So state x naught is said to be a controllable. If all initial states are transferable, then we can say that the complete system is a controllable. So system said to be completely controllable. Otherwise, if not we cannot able to transfer from initial state to some other state, then we can say the system is uncontrollable. So necessary and sufficient condition of this controllability is this matrix. Controllable matrix U can be represented as equal to G into f square G dot dot f to power n minus 1 into G. If we have to calculate the rank of this matrix, if should be the order of the F matrix, then we can say that the system is a completely controllable. We have to calculate the U matrix, then we have to take the rank. If rank of the U matrix is equal to the order of the F matrix, that is the system F matrix in discrete domain, then we can see that the all system states are controllable. How we are going to derive this one? We have to give the proof. So proof is the solution from the equations. We can see xk is equal to fk x naught plus, this is the solution which is already derived in the previous lectures. So here you can see the G is the n by 1 matrix. Here one input we have considered. We have to find GEF to power n minus 1 into G. So this is also, so we are putting k is equal to 1, k is equal to 0, k is equal to 1, k is equal to 3, like that up to n minus 1. When we are putting, so we are getting the same form. So we can write in the, this is the, when combining, so we are getting U equivalent to this form. Since the condition of the rank of the controllability matrix is n gives the sufficient condition to complete. So here you can see letter x naught is initial value, xn is the final. So here we are putting the same equation. You can see. So in generalized form, when we are putting this equation, you can see f x to power 1 minus f naught. So this is the U matrix we are getting. So we can find the rank of this matrix, that is equal to this one. So it is the, we can find the system is a controllable form. Similarly, we can define the observability. If the knowledge of the input uk, uh, where k is like start from 0 to n minus 1, with n is a finite positive integer, so output yk with a finite integer value from 0 to n minus 1 is sufficient to determine the all states of x naught. The state x naught is said to be observable. So for a sufficient input within a finite integer value, the output of the system yk is measured using the inputs and outputs, that is the, we can say the x naught, then state x naught is, we can say that the observable. Suppose we have to the input for the finite difference and output. From the input and output, we can determine the states of the system. Then we can system set as a observable. If all initial or all state variables are measurable, then we can say that the system is completely observable. Here we are considered only one state variable. For the one input and one output we are considered, and using these inputs we can corresponding, we can calculate the first state variable x naught in finite interval, and if all other states are can measure using the input and output, so we can say that the system is completely observable, otherwise is unobservable. So this is the necessary and sufficient condition v matrix we have to calculate, that is cf c to power f square into c into f to power n minus 1. We have to calculate the rank of this one. If we are getting the rank is same as the order of the f matrix, then system said to be controllable. So this matrix we can derive from the output equation. So output equation we in discrete form already derived. So here we have to putting k is equal to 0, k is equal to 1 up to kn minus 1. So we are getting the same, and we have to segregate in the vector form, so we can get a final solution. This is the vector form. So here we are combining these are c, cg, ce into f to power n minus 1, f to 1 minus 2. So we are combining, another is the x naught. So this is the v. When we are taking the rank and we are getting the rank equal to n, that is equal to order of the system, then system said to be controllable stable. In the condition that the rank of the observability matrix is n gives the sufficient condition for the complete observability. In previous two sections, we observed that the system matrix is observable canonical form of the system is a controllable canonical form, and similarly matrix B is the observable we can transport. So system matrix in the observable we can transport into the controllable. If a system matrix we have given, we have derived, that is a controllable, and we can transport into the observable form, so that is called a duality. Suppose a system is represented in the controllable form, and we are representing another system that is observable. So we can say that the system matrix A here and in controllable form, and system matrix in A in the observable form, both are the same, but the input matrix is the different. So in controllable form it is a input matrix, and in observable form this is the output matrix. We have to transpose. So C and B is the just changing. So that is called the duality of the system. So various canonical forms. This is the controllable canonical forms. Here we are considering the controllable canonical form. So what are the representatives? So here x1 k plus 1 x2 k, x2 k plus 1 this one. This way we have to represent all the state variables, and x and k is written here in this form. When we are combining, an output is given this form. So when we are combining this one, we are giving the A represented in this form, B is the 1 and C is equal to 1. So we have to calculate beta, alpha and every terms in this one, and this is the representation of the canonical form. So I am not going to discuss here detail. This is the very simple, so you can derive or you can take the help of the text books, and you can consider the here how we are going to calculate beta, beta 1, beta n. So there are a few examples are there, you can go and solve. So this is the transfer function is discrete domain, so we have to apply and represent. So using this one, this is the delay. Here we can represent z to power minus 1. This is the z to power minus 1. This is z to power minus 1. So in this form, this is the delay. And these are the summation terms. Then this is the observable form. So same we have to apply in the observable form. So here you can see x and k plus 1, this form, x and k plus 2, this is the form. Same we are writing here the yk we can retain, and finally we can write f, g, c, k in observable form. So you can see, so just we are taking the transpose of the controllable form, so we can get the observable form. In observable form, system matrix can be taken in the control form, only we have to consider the transpose. And G matrix, which is called as Duality theorem. So G matrix is the C matrix in the control form, and C becomes a B matrix, and D is the same. So here we are given the input, this is the A observable form. Observable form state equation is the dual of the controllable form. Now we are going to Jordan canonical forms with the distinct poles. Means all the poles are the different. So here the distinct poles base they have given the transfer function. We have to consider the both are the same order. So we have to fractional, we have to reach a fraction. So we have to calculate beta naught, and we have to apply the partial fraction. We have to equivalent A, B. So this is the lambda 1, lambda 2 is the distinct poles. So based on this lambda we can write in this form, G this is the one, and C will be R1 R2, this is the R1 R2. We have to calculate using the Z partial fraction expansion, and this is the A diagram. So we can write this is the Z transform, Z inverse, and these are the single terms are writing here, and we can summation. If the poles are the multiple, then we have to consider the multiple conditions partial fraction. So you can just here apply, and you have to calculate the matrix. So this is the m by m matrix, that is have the distinct. If there is a multiple, so this is the zm plus 1 to zn. So these are the multiples. So there is no. So here 0 0 to 1. So we are getting, and here 1. So in this way we can calculate every term. So this is R11, R12, R1. So you can say this is the in the form of the lambda. So 1 minus z minus lambda 1 to power m. M poles are the multiple. So we have to here put the in this form. So this is the all about the multiple figure. So you can take the reference books if you are finding any difficulty. So you can contact me. So I will provide the solution, or I will give the extra lectures regarding the this canonical representation. So here we are considering one example. So GZ they have given. So find 3 different solutions. So here A, so we have to represent in the controllable forms. A, B and C already calculated, and we have to take the just inverse. This is the observable form, B and C. So you can see C becomes B and B becomes C in transpose form. So this is the observable, and this is the Jordan form. Here the 2 distinct poles are there. So this is the Jordan form we represents. That's the 2 simple second order way I have considered. So you can apply here. So in this we can summarize here. So in this lectures we already discussed the controllability and what are the conditions for the to check the controllability of the system in discrete domain, then observability definition, then its conditions, and this discrete state space representation is represented in canonical controllable canonical form, observable canonical form, Jordan form, and also we discussed what are the duality theorems in discrete state representative. This duality theorem is same as the continuous domain. So this is all about this lectures. So thank you.